again, everyone. In this part of our lecture, we are going to dig deeper into the mathematical formulation of MPCs. I have already written down the main things that we need to consider. As you can see, there's a kind of great analogy between the MPC and the optimal control problem formulation that we have introduced last week. And in this specific part of our lecture, we are going to dig deeper into the model of your system. And in the next one, we are going to discuss the rest. The MPC is in the topic of, is in the focus point of our today's lectures. And of course, the way that we define our system may be different. For example, we have nonlinear dynamics. We could have nonlinear dynamics in our systems. We could have time varying dynamics in our systems, or maybe, let's say, relatively easier, we have a linear system in hand. And now I would like to briefly mention about the main options that we have in terms of how we can formulate our system mathematically. So, of course, they are not, let me say, MPC specific. We can use this type of formulations in any kind of system for our problems. But the things that I have listed down here are most of the time, let me say, popular ones. First of all, we may have a linear dynamics in our systems, and here we have the x dot is equal to f plus g u, and f and g is based on the x and t values. And we have a different type of output formulation that comes from another formulation, which is h here. So this can be accepted a kind of relatively complex one. And the other one that I would like to mention is linear time varying system. So in this case, we have linear system dynamics, but the dynamics of the system is changing over time. And we can understand this over the structure of the system matrices. For example, here in A is dependent on time variable, also B, C, and D. So this is a representation of a linear time varying systems in state space domain. And then, of course, we have linear time invariant systems. So this means that your, let's say, structure of system is not dependent on time. It's invariant of time. And how we can understand this, for example, in the system matrices, we don't have t variable anymore. So we have a kind of static structure in this formulation. And of course, everything until here was in the continuous time domain. What happens in the discrete time? A kind of similar notation can be used in for discrete time models. And here means that the next variable and next state variable is composed of the current states, my current states, and the input signals that I'm going to apply to my systems, and the output is also coming over the same representation. So we are going to focus more on the linear systems and more specifically linear time invariant and discrete models here. But of course, your system may not be directly fitting into the scope of linear time invariant representation or discrete time model representation. Then you could still do something to do, and this can be named as the linearization. And I'm going to briefly mention about the linearization options in the next minutes, and why we are making this. If we have a linear time invariant model in hand, we have quite lots of tools to solve our optimal control problem, and it's quite easier and quite less time consuming in that sense, so that if we can get a nice linear model of our system, everything rest should be relatively easier. Of course, you should have considered lots of other things, but if we have a linear time invariant model, life would be relatively easier for you as a designer. Okay, so then let's continue with linearization options. In terms of linearization, of course, we have also several options in hand, and I have just listed some of them. So first one is the Jacobian linearization, the other one is successive, and the last one is the feedback linearization. Jacobian linearization is basically linearizing your system around a certain equilibrium point, so based on the Taylor series expansion. It's relatively easy to derive, but it's valid around this equilibrium point. If you have larger perturbations, the performance of this one could decrease significantly. And the successive one is repeating this process in successive time frames or so, mostly shares the same principles. And feedback linearization, there are also two options in the feedback linearization, state and output feedback linearization, but it targets creating some new fictive variables and map between your current states to new artificial states. So the overall system between this fictive input signal and the actual states or actual output becomes shows themselves as a linear systems. And this, the last one, this feedback linearization, proposes better options in terms of practicality. Okay, so then let's slightly dig deeper into the Jacobian and the feedback linearization parts today. So, in the case of Jacobian linearization, informally speaking, what we are aiming to create is, for example, let's assume that we have an original fx signal, something like that, and we have an operating point or equilibrium point that shows itself in the form of x dash. And our intention is to linearize the system around this working point. And as you can see, so since this is a kind of basic example, the fx can be directly linearized as ax and plus b. So this is what is intended to be done. And in order to realize that, so we need an additional variable here, and we need to take the Taylor series expansion of our original system fx and evaluate it on the equilibrium points x and u. So this gives you a linearized system model at the end of the day, but you should be careful because, for example, if your actual working points, operational points increases, or you have larger perturbations in your systems, for example, you hit somewhere over here, the system's dynamic at this point and the actual linearized model is behaving totally different. It's because of that if you are really working around a working point or equilibrium point or so, this can work fine, but what I'm trying to say is that you should be really careful when you are using this Jacobian linearization. Another thing that you can do in terms of linearization is the feedback linearization, and as I have previously mentioned about that, there are two main options. The first one is the input to state feedback linearization, and I have tried to sketch the main diagram of it here. So basically we have our system structure here, which is nonlinear, as you can see from the representation. And what we are aiming to find is a kind of map of the states to an, let's say, additional variable z, and using this z and the feedback, let's say, control structure, we are getting an artificial variable v, and at the end of the day, our system from v to x seems like a linear system. And in order to do that, of course, we need to determine this alpha x and the beta x and use this new artificial variable v here, and then only this generates the let's say compensated input here. So this basically, this structure here compensates the nonlinear dynamics of our original nonlinear system based on using this map tx and this new variable z, so that you can use this new system formulation in your MPC formulation and then remap it to the official ones and apply the generated input signal to your system. So this is one way of doing things, and in the other one we can apply input-output feedback linearization. So I have again tried to sketch the main diagram of it. So we have our system and we have state feedback compensator rule here, and this rule is basically I represented here. So there is some interesting terminology here. So this LFH means the Lie derivative of your x function, and R here is the relative degree of your system. And when you apply this control law at the end, you get a linear system structure from your, again, artificial input V to your output Y. So by this way, again, you can use linearized system model in your MPC formulations. So this basically concludes this subsection of our lecture. In the next one, we are going to continue with the other things we need to consider in MPC formulation, like constraints, reference signals, and so on.